right, here's an example from that last theorem on page 2. And it is this: find a closed interval that contains the value of that integral. Find a closed interval that contains that value. So the first thing that we need to do is to find the little m and the big M, which are the maximum and minimum values of that function. And the function is x squared plus 1 to the 2/3. So much stuff is coming back to us today. It's very exciting because in order to find the maximum and the minimum value of a function, we need to do a derivative. So we need to find f prime of x. Let's pull that 2/3 down in front, times x squared plus 1 to the negative 1/3, and then times the derivative of the inside, which is a 2x. And then let's clean this up a bit and write this negative exponent piece back in a denominator. So we'll have 4x over the denominator. We'll have 3 times an x squared plus 1 to the 1/3. All right, now look where f prime of x is equal to 0, or f prime of x undefined. We don't have to look where f prime of x does not exist. That happens mostly in piecewise defined functions, and we don't have that, so we're just not going to look. All right, f prime of x equal to 0. That's where the numerator would equal to 0, so that will occur at x equals 0. F prime undefined is where the denominator could equal 0. That has to be where this x squared plus 1 is equal to 0. And x squared plus 1 can never equal 0, so there are none here. All right, now here's where you also have to remember that we do have a closed interval. Our closed interval here that we're looking is between x is negative 2 and x is 1. So this is an extreme value theorem, which means that we need to set up a t-chart and look for maxes and mins at the end points, which were negative 2 and 1, and the critical number, which is only 0. And when we evaluate, we're looking at x and y. This is the original function. So plugging a 0, let's do that one first because that's easy. 0 squared, 0 plus 1 to the 2/3, that's 1. Put a 1 in here. That's going to be 1 plus 1, 2. That's 2 to the 2/3, which I'll help you out here decimal-wise. That is 1.587. And negative 2 plugged into the original, that's 5 to the 2/3, which decimal-wise is 2.924. All right, now there is a maximum at x is negative 2, and the maximum value is 2.924. This is what we're looking for. That's the maximum value. And the smallest y value over here, there is a minimum at x equals 0, and its value is 1. That's the minimum value. So we know then that from the previous page, again, that little m times b minus a is less than the integral from a to b of f of x dx, which is less than big M times the interval b minus a. And substituting in the numbers as appropriate for this problem, little m is 1 times b minus a, that's the length of this interval, 1 minus a negative 2, less than this integral from negative 2 to 1, x squared plus 1 to the 2/3 dx is less than big M, that's the maximum value. I'm going to write that as 5 to the 2/3 times b minus a, still 1 minus a negative 2. And this leaves us with 3 is less than this integral from negative 2 to 1 of x squared plus 1 to the 2/3 dx, which is less than 3 times 5 to the 2/3. All right, which decimal for this one is 8.772. So this is an answer. As is, another way to write this is that the integral from negative 2 to 1 of x squared plus 1 to the 2/3 is between 3 to 8.772. So you're putting that as a closed interval. Oops, I gotta go back. And you know what? You might want to do this. I think I just realized right now that these should have been closed. So can you go back to the previous page and just put that in as less than or equal to instead of strictly less than? If you would do that and fix that error so I don't have to go back and re-video that whole page just for that one little piece, I would appreciate it. Either one of these is acceptable ways of writing this. Okay. All right, now the next piece we have is the mean value theorem for integrals, which says the integral from a to b of f of x dx is equal to some f of c times b minus a. Oh my. Let's take a look at that and see if we can figure out what this shows visually. Let's put some function up here, y equals f of x. And let's put some interval in here from a to b. Okay. All right. Now, clearly, this part right over here is talking about the area underneath that curve from A to B. All right, so if we visualize that here, that's this. All right, this part over here, f of c times b minus a. Well, b minus a is the width, same width as that function, and this f of c is a height. And it's a width times a height. That's a rectangle. So this over here is the area of a rectangle that's got the same width. All right, now f of c, that c value is somewhere in here. Let me see if I can kind of maybe guesstimate where it is. It's not always smack dab in the middle. We make a rectangle with that height. What this is saying is that the area underneath this rectangle has the same area as the area underneath that curve. So again, it says that the area underneath this rectangle with this height, f of c, has the same area as the area underneath that curve. Area underneath that rectangle same as the area that's underneath that curve. So it's kind of like this area piece right here would fill in that emptiness down here, and this one also would have to fill that in. I'm off a little bit, but not too bad. All right, if we write this out in words, here's what this mean value theorem says. It says that there is some C between A and B such that the area of the rectangle with width B minus A and height f of C is equal to the area under f of x on the same interval. All right, and an extension of this talks about the average value of a function over an interval. Okay, average value, value here meaning height. All right, normally we think of finding the average by adding up a bunch of things and then dividing by however many there are. And if you look at this picture here, how many heights are there in this interval from A to B? Well, there's an infinite number of heights, so we can't possibly add them all up and then divide by an infinite number. But what we can do is say that that height, f of c, that height is the area divided by the length of the interval. This expression right here is average value. And if you think about this, if you think rectangle, if this is the area of a rectangle, and you divide it by its width, area divided by width is height. Well, we just don't have a rectangle, so the area of the whole thing divided by how wide it is will give us a height that would give the same area. So that's kind of, if you could add up all of those heights and divide by however many there are, that infinite number, you would get that particular height. This expression, average value of function, very important. Please memorize that. Page 4 will have an example of how to find the average value of a function.